This is about rejection regions.
Thank you so much, Aiden. We're going to jump over to the other one now, and we're going to deal with just that topic. All right, so let's see. All right, so this is 8.1, rejection regions. All right, and I'm going to remind people that these rejection regions, they are set by the claim H1, the alternative hypothesis. The size of the rejection region is set by the level of significance alpha, and the position is set by the critical value or values depending on the test. All right, so let's take a look at an example or two. So I'll remind people that the null hypothesis is always written with an equal sign regardless of the less than, equal, greater than or equal to statement. The alternative hypothesis is always a strict inequality. For my first example, I don't really care here so much about values as the direction of the test. So this is one of the left tail tests right there. So what that means is that in terms of a picture and our distribution, be it Z or T or perhaps some other distribution, we have a critical value that defines what we call the rejection region. And that's set by the critical value. And then what I need to do is to plot the test statistic. So the idea is to plot that test statistic somewhere on this continuum. Maybe there, maybe there. Now, if we plot it in here, we're going to go ahead and keep the null hypothesis. That's if that test statistic does not fall in that shaded area. If the test statistic does happen to fall in the shaded area, we're going to keep the alternative hypothesis. And that's what happens if the test statistic falls in the rejection region. Rejection being rejection of the null hypothesis. Now, let's take a look at a couple more examples. Suppose my alternative hypothesis is written with a greater than. This will tell me I have a right tail test. And in terms of a picture then, that rejection region, remember I like schematic sort of pictures, falls entirely on the right. That alpha is the size of that rejection region. And then I'll go ahead once again and plot the test statistic. And again, there's a couple of places that it might fall. If it falls in this region, we're going to go ahead again and keep the null hypothesis. On the other hand, it might fall there. If that is the case, then we're going to go ahead and keep the alternative. What about the two-tail test? Here, that rejection region is split equally between the left and the right tail of the distribution. Each of the little pieces has alpha over 2 of area. And once again, you know what we're going to do. Plot the test statistic. So that's what we're going to do. And again, it could fall in a couple of different places. If it happens to fall somewhere in this part, if that is the case, then again, we're going to go ahead and keep the null hypothesis. That's what we're going to do. And there's a whole bit of detail about how we go about doing that. On the other hand, it's possible that the test statistic could fall closer to the tails. If that is the case, then we're going to go with the alternative hypothesis. So, to summarize, alpha tells us how large those rejection regions might be. The critical values tell us where they begin and end. We'll plot the test statistic relative to those rejection regions, and that tells us how we're going to determine the outcome. If we go all the way back to the analogy of a trial, not guilty is here in the center, but if the evidence is overwhelming enough, we dispense with the not guilty and we go with the guilty. Thank you so much for your time. I'll have more detail later.